Hello everyone and welcome back. Now, for the past few lectures, actually pretty much everything in this course so far, we have focused on what I'd like to call matrix methods. These are methods for dynamical system analysis that are inspired by linear algebra. That means that they rely on things like the singular value decomposition or the pseudo-inverse. And in particular, almost everything boils down to some version of extended dynamic mode decomposition or just dynamic mode decomposition, however you'd like to think of it. What I would like to do from this point forward now in this lecture series is look at nonlinear methods. That means methods that are not just coming from linear algebra. Now, linear algebra inspired methods are great because linear algebra is one of the most well understood areas of mathematics. We can get proofs in that domain. We can get decay rates on certain estimations in the amount of data that we have. There's almost nothing that is left unexplored when it comes to these linear algebra inspired methods. Nonlinear methods are the Wild West. And what I mean by nonlinear methods, going forward, we are going to talk about neural networks, right? So neural networks are a way of sort of recasting a lot of these problems that we've already looked at using these nonlinear approximations for functions. And that is really the neural network itself, right? Neural networks, machine learning, artificial intelligence, all of these things conjure up some wild, maybe big brain ideas in your mind. But really what I want to do in this lecture is really just show you that it's just math. It's a very, very simple density result that lies at the heart of all neural network methods, okay? So this lecture is going to be a theoretical introduction to the mathematics behind machine learning and neural networks. In the next lecture, we're going to look at the topics in training neural networks. So this means things like automatic differentiation, backpropagation. How do we actually program a neural network from scratch? And after that, we're going to switch over to very powerful machine learning training tools and softwares. In my case, I'm going to use TensorFlow, but you could use PyTorch or JAX or whatever your favorite is. And we're going to let them do most of the work because these are software packages that have been highly optimized to implement all of the theory that I'm going to spell out in the next two lectures. Now, here's where I want to start. I want to start by talking about density in terms of function spaces. So for example, if you remember my lecture series on Sturm-Liouville theory, I gave all of these nice results that showed that if you have a function f of x, typically it has to be in L2, but let's just imagine it's a continuous function. If you have a function f of x, then you can write it as an expansion of these orthogonal functions. Let's just say ci. Typically this has to be an infinite, I equal to 1 to infinity. Infinite expansion in some basis functions. Now, the typical idea or the typical application of this that you learn is Fourier series. They could be the complex e to the ix, e to the I kx or something like that, or they could be sines and cosines, whatever you want them to be. But of course, these could be Chebyshev polynomials, Legendre polynomials, more generally Jacobi polynomials. They could be Bessel functions. You know, there are all kinds of ways of doing these basis expansions. And if you have, say, an unknown function f of x, then expanding it becomes a question of identifying these coefficients in the span. And effectively, our numerical methods that we now call, say, spectral methods or Galerkin methods, they rely on taking an unknown function f and expanding it in some known basis and trying to find these coefficients. Now, this is a very powerful way of doing analytical math. And by that I mean, writing stuff down, getting explicit answers. But there is another way that we can do this that inspires neural networks, because doing this with neural networks typically requires a whole bunch of these C's. And what we really want is to get away from using different functions every single time, right? So of course, to make these expansions better and better, you have to use more and more functions in this expansion, and that means you're using more and more different functions. The beauty of neural networks is they are inspired by a single function using itself over and over and over again. Here's what I'm going to do. I'm going to lead by example, okay? And here's my example that I want to use. I want to think about a function from, let's just say, the unit interval into the reals, and I want to look at an approximation of this function. Now, I'm going to sort of work through this piece by piece. I want to approximate it with continuous functions. Of course, I'm going to assume this thing is continuous itself. And the end result here will be a density result in the space of continuous functions. Now, remember, density means that close to any continuous function, there exists a function in my dense set that can be arbitrarily close to it. Now here's a really simple thing that I want to do. I want to think about a step approximation to my function f. Okay, so let's just think about this for a second. Let's draw it all out. Here's my function f of x, right? So let's just say, let's go all the way back down to 0. Here's 1 right here. Now, you probably remember this from your calculus class, right? How do you approximate the area underneath this thing? Well, you put a bunch of rectangles underneath it, right? You remember how to do this. This is the sort of basis of Riemann integration. Okay, so here's my little rectangles. They should all be the same width, but of course, I'm drawing this freehand, so give me a break, please. But here's what I've done, okay? If I think about the actual function that comes from these steps, what I've actually done is introduced a step function approximation to f. I'm going to call it s sub n. N is going to be for the number of rectangles underneath this. It's going to be a function of x, and here's the real definition of it. It's going to take the value f of 0, so it's a left Riemann sum, left endpoint Riemann sum, on the entire interval, so when x is between 0 and 1 over n. And then it's going to take f of 1 over n when x is between 1 over n and 2 over n, right? And you can keep doing this, and it's going to take f of 1 minus 1 over n, that's the last point, right? It's this guy right here, on the interval 1 minus 1 over n, and we're going to go all the way up to 1. We'll close it off. That's fine. Okay? This is my step function, s here, and it approximates my function f. In particular, what I know is that if n is large, then I'm trying to write this maybe informally, but the difference in the supremum norm, so I'll say the infinity norm, which is just the maximal pointwise distance between these two things, let's say f of x minus Sn of x is small, right? It can be made as small as I want. So, you can do this with epsilon deltas. For all epsilon greater than 0, there exists a capital N large enough so that when n is larger than capital N, this thing is small. Here's me doing this with my nice hand-wavy fashion, right? So I'm doing it informally, but that's okay, right? This is just a video for you to understand the basics. But here's the thing. Okay, so that tells me that the step functions can well approximate any continuous function. In fact, if you want to prove this fact, try it out, pause the video. You can argue by the fact that the domain is compact, so continuity implies uniform continuity. You can argue from uniform continuity how you get this result. Okay, so I'm going to leave it as an exercise, a really fun little thing for you to try out. But here's the problem. This is not continuous. So, okay, great. We approximated a continuous function by something that's not continuous. Continuity is like one of the most desirable properties in all of mathematics, right? Roughly, continuity says points that start close together sort of stay close together. There's no real jumping in the function. So we would like to do a little better here, okay? And what we would like to do is try and approximate this function f by something continuous. here's where Cybenko's result comes from. So Cybenko, I believe this is around 1988 that he introduces this. Cybenko's result is one of a massive now collection of results that are called universal function approximations. Cybenko, again, this is like the late 80s when Cybenko does this. This is the foundation, at least in my opinion, of all machine learning, at least in modern machine learning. Again, this is back in the 80s when he does this. But what Cybenko says is I want you to consider what are called sigmoid functions, okay? So let's say I'm going to call them sigmoid functions, which are, I'm going to use the Greek letter sigma for this. Sigmoid functions satisfy, so such that the limit as x goes to minus infinity of sigma of x is equal to 0. The limit as x goes to plus infinity of sigma of x is equal to 1. And it's increasing. So sigma prime of x is greater than 0 for all x in R. You can use greater than or equal, but here's the basic idea. Sigmoid functions look like big S's. There's my sigma of x. Okay? That's what they look like. And in particular, here's, you want some examples? Here's one for you. This one we call the logistic function sometimes because it's the solution to the logistic dynamical system. There's one sigma function. Here's another one. Sigma of x is, let's do 1/2 arctan of x plus 1/2. I just had to shift it with the 1/2 to put it between 0 and 1. But again, that's an S-shaped function. That'll do. And so here's what we're going to do. We're going to actually use sigmoid functions to approximate every other function in this space. Okay? So here's how we'll do it. My first result that I have on the board tells me that step functions will approximate every function that's continuous on the compact interval, right? So that means if I can use sigmoid functions to approximate any step function by the triangle inequality, sort of by transitivity almost, sigmoid approximates step, step approximates continuous. So therefore, sigmoid can also approximate continuous. Again, sigmoid functions are continuous. And here's what I want to do. I'm going to take an arbitrary step function, okay? So let's consider, here's my step function on an interval. I'm going to say alpha to beta. This is just a little indicator function. So if x is between alpha and beta, it's equal to 1. And if x is outside, then it's equal to 0. All this thing is a little top hat. That's it. Nothing fancy, okay? And so basically, this function right here, right? So this tells me that my Sn from before can actually be written like this. It's written as the sum from k equal 1 to n of f of, now let's see what I have here, k minus 1 over n. It's just because I'm using left endpoints. And then s of k minus 1 over n to k over n of x. You can close this off. It doesn't matter because of the jump. But now this is looking a lot more like my basis expansion that I had up here, right? It's feeling a little bit more like classical mathematics. What I'm going to do is I am going to approximate any arbitrary step function like this, little top hat here, using a sigmoid. And here's what I want to do. Let's consider a sigmoid with rescaled space. I'm going to rescale space by a function w. And take a look at this. The limit as w goes to infinity of this thing, right? Well, if x is positive, it's getting taken to 1. So this is for all x bigger than 0. And if x is negative, it's going back to 0. But think about what this thing is now. This is a Heaviside function, right? It's a single step. It's half the top hat, right? So that means that I'm going to do this sort of very roughly, right? If I take w big, so let's say w very large, w much bigger than 1, that means I'm getting close to the limit, but I still have a continuous function here. The limit is discontinuous. Then the step up to alpha here, right? So then I could do this. From alpha up to, let's just say to the endpoint of the interval 1, because that's as far as we care about, I should have this approximation. I should have sigma of wx minus alpha. I shifted the domain so that its jump now happens at alpha. W is very, very big, so it's a very steep but continuous transition now. And let's do something else. I could do this as well. I could go from 0 to beta, right? So this is a flat piece from 0 to beta at 1 and then a step downwards. Well, how can I put this piece into this? Well, this would be 1 minus sigma of wx minus beta. 1 puts me up where I need to be. The minus, okay, so the minus, when I am above x is bigger than beta, this thing pulls me down, right? Because this value should be close to 1 when w is huge. So 1 minus 1 pulls me down to 0. And I get a nice transition downwards. But then this 1 could take the place of another sigma function. So it tells me that if I wanted to put both of these, or just take this little compact interval from alpha to beta, here it is, alpha to beta, this could be the step up at alpha minus the step down at beta, right? And so that means that this expansion right here can be replaced by these smooth steps, right? So they're not perfect steps anymore, but they have a nice smooth, step up. These things are continuous. I can use, this should be maybe approximately equal, pardon me, right? Maybe I should be a little bit more careful here. These are approximations. The bigger w is, the better this approximation is. But that means that if I replace each one of these things by a step up minus a step down, using potentially different w's to get better approximations depending on where you are, and different alphas and betas, I can approximate every single one of these steps using these sigmoid functions. Now here's the beauty. This works for every sigmoid function, right? Just has to satisfy Cybenko's assumptions here. And it's self-similar. What do I mean by self-similar here? It's only using sigmoid functions. That's the only function in the whole basis expansion. Up here, remember sines and cosines, you have to use different frequencies. It's different functions. Chebyshev, right? What's the 100th Chebyshev function? That's a very hard thing to calculate. But what's the 100th term in this expansion? It's just another sigmoid. That's the beauty of this. This is what's called a universal function approximation, a universal function approximator, these sigmoid functions. And in fact, Cybenko's results go even further. Cybenko's results actually apply to any dimension of domain. So I'm just going to try and sort of squeeze this in here. But Cybenko says that if you have a function f, let's say from 0, 1 to of some dimension m into R, you can approximate it. So then you can approximate it by a function g of x that looks like this. It's the summation from k equal 1 to, let's say, n, which n is the number, like the sort of degree of approximation here, of a vector vk and then sigma wk dotted with x. This is a dot product because it's a multi-dimensional space, and then plus bk, okay? So I know that I'm kind of squeezing that in. I don't want you to get confused. But the point is, you can approximate every continuous function, in this case on the unit square in m-dimensional space, using these sigmoid functions. And people have taken this way further, right? Let me just maybe squeeze it up here. You can actually do this for functions from, say, any compact set C into, let's say, what's the dimension? R capital N. So capital N dimensional space by a function, let's say, g of x. And I'm going to do a thing that we do in machine learning here. V times, sorry, this should be sigma. And then wx plus b, where v, okay, well, let's do w first. W is, I'm going to say, a little n by capital N matrix. Little n, like I said down here, or as you can see in this sum, it's sort of the degree of approximation. The bigger little n is, the better the approximation. I'll come back to that. V is in capital N by little n space. And B is in little n-dimensional space. And essentially, what we know from this is the bigger little n is, the better this approximation will be, okay? So this becomes the issue. Here I'm applying my sigma pointwise. So this is sigma being applied to each element in a little n-dimensional vector. So that means that little n, you expect it to be very, very large in the same way that you expect these step functions to be accurate when little n is very, very large. And so that means that, these approximations, they can always be done, but they probably require a very large little n. That's sort of the hidden dimension in here. Now, some people didn't like this result or wanted to improve on it because they said that's a lot of little n's. And in fact, what they started looking for is trying to pinch or trying to fix the size of little n. And what they started looking at was function composition instead. Okay, so I'm just going to erase down here so that you can see what I mean. I'm just going to squeeze it in. I know you hate me for this, but I mean, it'll be worth it, okay? So here, instead what people started doing is they started approximating with functions that look like this. G of x is some vector or some matrix WD, and then this is going to be times sigma, and then composed with WD minus 1 of sigma, WD minus 2 of sigma, right? And then you have all of these compositions. Sorry, this becomes plus BD minus 1 plus BD. Sorry. And basically what you've done is you've taken the original, what are now called neural networks, but I'm going to call them universal function approximators for now, and you compose them with themselves, right? And by composing these things with themselves, you could make what was already a maybe not so complicated function a lot more complicated, okay? Think about a sort of regular sine wave and then sine of sine, right? That is a way more complicated function. Then think of sine of sine of sine. That is an even more complicated function. And people started looking at these compositions. Here, D is another parameter, just like the size on the inside. D stands for depth. This little n stands for width, if you're coming at this from machine learning. But essentially, this is the foundation of deep neural networks, right? Because essentially what you're doing is you're taking what were original sort of Cybenko style neural networks and composing them with each other to make them deeper and deeper and deeper Okay, so when we come back in the next lecture, we're actually going to see an application of this, but we're first going to talk about how to actually train these neural networks, find the V, find the W, find the B, find the capital N that's going to make these things work well. So I'll see you all in the next video, everybody.